Now, today we're going to have a look at the first more modern systems you'll see on cars, which are distributor-less systems, right, ignition systems. We're just looking at three basic models here. If you can see the first one here, we have a coil, and you can see on it here, there's some sort of unit on it here. Now, what this is a ignition module or amplifier unit, as it became known. This is a coil that doesn't have an amplifier unit, so it's just a standard coil, and the same on this one here. Again, no amplifier unit. Now, the difference being between one with an amplifier on it and one that doesn't have it on it is where our control is, because remember, we're still want to control the primary circuit. If a manufacturer puts the amplifier on it, he needs a signal to come to the base of the transistor here to turn on and off the primary circuit. So control of that coil is inside this amplifier or ignition control module, which is sitting on top of the coil. For this type of coil here, there is no control on it. So the control must be somewhere else. The only other place it can be is in the engine ECU, whereas an awful lot of manufacturers are using that type as well now. So it is direct control here onto the primary winding. Again, the difference being here, if we look at the ignition module here, if you can come in and take a look at it here, if we see inside here, we see there are 4 pins. They are mainly to do with this ignition control module here and the primary winding. This type here, we see there are just 3 pins on it, right? So that's no ignition control module, just simply direct control of the ignition primary winding here. And the same over here on this one here, we have a 3-wire here. So again, direct access to the primary winding here. When we're testing these coils, because this unit is in between here now, so I have engine ECU giving direct feed onto the ignition module, and the ignition module or amplifier controls the coil, which is underneath here. This is the meat in the sandwich here, right? Whereas on this type here, we have direct contact onto the actual primary winding. So we don't need anything else. We can get straight in onto this here. And again, like with the old barrel type coil here, if we have direct access to, if you remember, these two are direct contact with the primary winding, and then we went from the center tower to either side of it to get access to the secondary winding. If we look at this type here in the middle, we'll start with this simple one. If we have 3 wires in here, we're going to take a look at what they are. Now, there can be different variations of this system. If we take a look at the board here, we've drawn it out here. So, for that particular coil here, there are 3 pins, 1, 2, and 3. And remember what I said, that's direct control to the primary windings. Now, inside that coil, there are 2 primary windings. One primary winding to the left here controls, if you look up here, coil A we'll call it, and we look to where it's going to, right? So coil A goes to cylinder 4, the other side of the secondary winding goes to cylinder 1. Across on the opposite side, we've coil B. Now all in the one unit, here's our one unit here. Again, one side of the secondary winding goes to cylinder 2, the opposite side goes to cylinder 3. Well, it has its own primary winding here. So if I want to control that, if I said, right, easiest way to do this is give this cylinder or wire 2 here a positive feed, so a 12-volt feed in. Now I can control 1 and 3 back at the ECU through a transistor, either closing the circuit and letting it go to earth, so we have a positive feed into the middle. Remember, the voltage is all the way around here to back out the wire and goes back to the actual ECU where it is stopped by the transistor. It's looking for earth for a current to flow, but the voltage is still there. When I close the circuit, current will now flow through the center pin 2, through this primary winding and back out and go to earth, which will start current flowing through the primary winding, and then we're back again to our building up the magnetic field here in it. In the middle here we'll have our soft iron core, and when I break the circuit for the current flowing through the primary winding. I self-induce into that, and at the same time mutually induce into the secondary winding here a high voltage, low current, and off it goes, out one side. And nearly all the time what they do with this type of coil is, because it could fire 1 or it could fire 4. So what they'll tend to do is put a diode on it here to make sure that the current always flows in one direction. Now we're going to come back to that primary winding or secondary winding in a second. The same happens here. This, we break the circuit for coil A. If we look over to coil B here, we make the circuit here for the primary winding coil B, saturate up the primary winding, and then break the circuit again, self-induce and mutual induce, and off we go again. Shoot one side, and put a diode on it to make sure it's only going to flow in one direction, and we'll get a spark down through the secondary windings. Now, let's take a look at the coil itself, because if we're looking at this diagram, if I wanted to test the primaries on it, I have access to them through the 3 pins here. So remember, a coil is just a coil of wire, and if I want to test it, all I'm going to do is use an ohm meter. So again, disconnecting of the coil here, turn our meter onto ohms. Now again, with this meter, it's an auto-ranging meter, which means it'll run from point something of an ohm all the way up to mega ohms. If you don't have an auto-ranging meter, you will have to manually select on the dial what you think it's going to be, and this is where your knowledge is going to come in. If you remember back to our primary winding on our barrel type coil, we had a very, very low resistance winding for our primary winding. Our secondary winding, which was between either there and there or there and there, was a high resistance winding due to the fact that there were so many more turns of windings of wire in the secondary. So you should have in your head at this stage known each primary circuit is going to be relatively low. We're talking less than, in the vast majority of cases, 2 ohms. Older type 1 maybe up to 1.6 or so. Newer type 1 for the wasted spark system, lower than an ohm in an awful lot of cases. So if we're going to test a component like this, remember we disconnect our wiring plug off it. On our meter, remember if I'm going to test anything for resistance, I have to zero out. So remember, zeroing out, we can see when it's open circuit, it shows me OL. When I close the circuit, it's going to give me the resistance of the leads. Now, if I'm going to measure resistance in a coil, I don't want to take part the leads resistance. So I'm going to zero out and see what's in it and subtract that away from what I measure. So we've 0.1 of an ohm inside these leads. And from our diagram, if I go to the center wire, remember there's no polarity in resistance, so if I go to the center pin and go to the either side of the pin, what we should see on the meter is the resistance of one side of that primary winding. Where are we? Sorry. So we're up here now, 0.6 of an ohm for one side, minus the 0.1, which gives me 0.5, and then the opposite side will just move over. Pin 2, remember, is going to be our common point, and we're going to pin 3 at this stage in the game. And again, over this side, we see 0.6 of an ohm minus our 0.1 brings me to 0.5 of an ohm. Now, give away on these, if you look closely at it, if you look at the shape of the actual coil itself, as a block it looks like one unit, but we can see here there's 2 barrels encased in it. So the barrel to this hand side, we measure from the center pin, pin 2, to the right hand side pin, pin 1, and we get the primary winding resistance of this one. When we switch over, we go from the center pin to pin 3, and we're getting the primary winding value of this barrel coil here. So it's essentially like having 2 barrels sitting one under the other like that. One there and one there. 2 separate primary windings, and in this case 2 separate secondary windings. But it's easy enough to measure that with a meter and say, okay, check your specs for whatever it is. Remember from our specs when we checked the barrel coil, it gave us a range between 0.9 and 1.5 ohms. Again, there will be specs for primary windings on this. You'd have to make sure your primary windings are falling inside the specs to guarantee that it is a good winding. Right? If it's outside the specs, you have to condemn it. Right? You have to condemn it. So, let's take a look how the system works. This is what they call a wasted spark system. Now, it's the first distributorless system. So our feeds in from where things are happening are coming from our crankshaft and our camshaft. We're going to power up coil A here, this side here. So we've got 12 volt constant feed here. Remember, when this is broken to earth, there is no current flowing through here, so no magnetic field gets created, and we do not mutually induce into the secondary. But once I earth this, I start to saturate this up and build up the magnetic field into it. Then the ECU breaks the earth for the primary winding. We self-induce into here, and at the same time mutually induce into here. Now remember, you can see there's way more turns of wire in this than there is in this. So we're going to step up the voltage. Normally, or as an average figure, you could take 100 times more. So if I self-induced into this when I break the circuit 200 volts, let's say there's 100 times more windings in the secondary, I'm going to multiply that 200 by 100. With 200, 2,000, 20,000. And off we go here, right? Spark comes out here, travels down the plug lid, and it's running. Follow it, follow it, follow it, follow it, follow it. Gets me to cylinder 4. Now the spark is going to jump there. Remember, it is a DC current, so it wants to get back to where it got created, and it got created in here in the secondary winding. So it'll jump across here and arc across the center electrode to the earth electrode, and that's screwed into the head. So it uses the head then for that tiny, tiny current that wants to get back to earth. So it'll make its way to this side here. It'll spark in that direction now, from the earth electrode back to the center electrode, travel back up the plug lid, back into this side of the coil tower, and now it's home. It's back here again. So, for each time it happens, it has to travel in a direction. So how does this actually work then? Because remember, our 4-stroke system. Intake, compression, power, and exhaust. If coil A is controlling cylinder 1 and cylinder 4 for spark, and coil B is controlling cylinder 2 and cylinder 3 for a spark, we're going to create a spark for cylinder 1 when it's going compression power. It's also, at the same time, going to give a spark through cylinder 4 for its return journey. But at that stage, it's not on compression power. It's more likely on exhaust intake. So, the spark across it makes no difference to it, which is why they call it this wasted spark system. Only one of the 2 sparks that each coil A and coil B, created at any one time is a useful spark and gives me power. And if we think most firing orders now are like this: 1, 3, 4, 2. If we look, we're going to spark cylinder 1, which is coil A. The next cylinder to spark is cylinder 3, which is coil B. The next cylinder is coil A again, cylinder 4. And the last cylinder is cylinder 2, coil B. So we're getting this time now between it, because we're going coil A sparks, coil B sparks, coil A sparks, coil B sparks. So the time we have in here for our dwell, which is our time to build up or saturate the magnetic field around that primary winding, we get extra time as compared to our original barrel type system. Because remember, this barrel type had to give me a coil for every single cylinder that I wanted to spark for. So its dwell time was greatly reduced. If I reduce the dwell time, I reduce the amount of magnetic field that I can have time to build up, therefore reducing the actual induction voltage into the secondary winding and giving me a weaker spark. So if I can space it out like this between cylinder 1, cylinder 3, cylinder 4, cylinder 2, I give myself the extra time that I need to make sure that I have enough energy built up in this primary winding, magnetic field built up, so it's good and strong. So every time it sparks, it's going to give me a good bright spark down through the secondary windings here. And the wasted spark system is probably one of the few systems where it is actually a true Faraday system. Remember, Faraday's experiment said there is no contact between the primary winding and the secondary winding, right? We saw on the original barrel type coil there had to be a connection to get that high voltage spark, low current back to where it came from. But on this one, we can see there is no connection between our primary winding and our secondary winding. It uses the head. Once it's jumped across in this direction from our original one, because remember, we're sending it down this way. We're making sure it goes this way. It can't come the opposite way. So by the use of a diode, we're sending it down here. We're sending it to cylinder 4. It's jumping across from the center electrode on the plug to the earth electrode. From the earth electrode, it's traveling through the head. Again, it jumps from the earth electrode now back to the center electrode on the spark plug and gets back through this spark plug lid and back to where it got created, which was here. And it does that the same for this side here. When we create the spark, we send it off with a diode in one direction, travels to cylinder 3, jumps across from the center electrode to the earth electrode, uses the earth electrode because it's screwed into the head to travel back up to cylinder 2, jumps from the earth electrode to the center electrode, travels back through the lead now, back into the coil, and ends up back here where it got created. So it is the one true Faraday system for all the systems really that we look at, or for most of the systems that we look at. Now, on the second coil here, still the same idea here, coil, except for we've put this ignition amplifier or ignition control module right in the middle. So, control of the primary for this type here, 3-wire one, is still a transistor which is controlling that primary winding, but it's not here. It's back down into an ECU somewhere. Whereas this one here has the actual control transistor inside here in the amplifier. So control of this coil is inside the amplifier and it's using the base of the transistor. I have 4 wires on this we already saw, right? But they are the 4 wires for the actual control module and the primary winding as well. But trying to pick up on what's happening here becomes slightly harder. Now, this is a Volkswagen unit and there are 2 tabs normally on this. If I squash the tabs together, I can remove the ignition amplifier off it, and we can see there on the bottom of it. If I remove it off, this is the amplifier part or ignition control module here, but I have 3 pins, 3 connectors, and we're back to exactly the same as this one here. Again, we zeroed out our meter and we found we had 0.1 of an ohm, so pick our center connector. Pick one side, because we can see clearly here, there's a barrel for one side here, and there's the barrel for the other. If I connect across it, I will pick up the primary winding resistance here. So again, 0.7 of an ohm minus the 0.1, again about 0.5, and go for the center one to this barrel now. We're picking up the primary winding here. So make sure you get a connection on it. So again, 0.7 minus the 0.1 gives me 0.6. So both look the same. Again, we'd have to compare that to the specs for that coil to find out is it inside its range. And now, once it's inside its range, we can say the primary winding for this coil is good, primary winding for this coil is good. Last little test on it now. Secondary. If you remember the barrel type coil, we went from one side to where the spark comes out. But for each coil, we have 2 towers now, right? Same as our diagram here. Here's our tower 1, tower 2, either end of that secondary winding. So if we want to test the secondary winding to see it's in good condition, again we come back, pick our two towers, go down inside it, touch off what we see here. So if you can zoom in on that, and remember this is an auto ranging meter. So what we see there is 4.00 kilo ohms. You can see just in the right hand top corner it's saying, giving the kilo ohm signal. So we should know that secondary winding is going to be. Remember, because there's way more turns of wiring. So one of the factors that causes a resistance in a piece of wire is the length of it, right? Because they're 100 times more, I'm going to have a lot more resistance in the secondary winding. So I should have that in my head. For secondary winding, all the time, it's going to be kilo ohms. Now, if I converted the 4 kilo ohms into ohms, I end up with 4,000 ohms for this side. If we see what the other side is, because this is a separate secondary winding on this, we see we've 4.05, again, kilo ohms. So 4,050 ohms is what I have here. Again, what we'll be doing with that is checking it against our specs to make sure we fall inside our range. If we fall outside our range, we have to condemn it, right? We have to condemn it. So we need our data specs to give me the final, is this yes or is it no? Is it good or is it bad? Same on this one here. If we go directly to it, this is, remember, one coil here, so always have a look and see where the barrel is. Here I can see the barrel is here. These two here are connected to the left-hand side barrel. So again, just touch off them. Let's see what we have in here. We have got 8.64 kilo ohms, so 8,640. And go to the second coil, we're going to check the secondary for this. So we've 8.75. Now remember, we tested the internal resistance of the leads on this. Once we get up into that kilo ohm section, the secondary section, that 0.1 of an ohm is going to make no difference whatsoever to whether I'm inside or outside the actual range, because it's so high now at this stage in the game. So that's simple testing of those wasted spark type coils. I don't need a meter, or I don't need a scope to do it. I can do it with a simple meter, check the primary, check the secondary, check them out, what I read off the data, and give a yes or no, a good or a bad for primary and secondary windings inside all of those coils. What we'll do is we'll take a look at, in the next video, what this looks like now. Because remember, if I'm probing one of these wires here, because I don't have, if my ignition amplifier unit sits on top of the coil like this, I do not have direct access to the primary winding. So I can't get a primary winding signal like we did from the Kettering type coil, right? Because I can't get exactly on it. If I have a 3-wire one and I do have access to the primary, I can get on and produce a primary waveform to check and see what it looks like. We're going to take a look at what both of those waveforms look like in practice. But remember, for this one here, if this is a ignition amplifier and I don't have direct access from the pins here to the actual primary winding, all I can do is check the primary winding on it with a meter, check the secondary winding with a meter, and then I want to have a look here at what signal is coming into this. Because remember, where the amplifier is here, the actual control transistor is inside this amplifier. So all I can look for on it is an actual on-off, like our Hall distributor unit, on-off square wave signal to the base of it. If I'm getting a signal to the base of it, and I have power and earth, I'd have to assume that the primary is good, right? Now I can check the secondary from either side. If the primary is good and the secondary winding is good, I should produce a perfect waveform for both primary and secondary. On this one here, I can actually physically get on to the primary winding, so I will be able to produce that primary waveform signal, not an on-off, because the on-off to the the base of the transistor is happening somewhere in the ECU out here. So I have direct access to the primary winding here, so I will be able to produce a primary winding waveform, not a signal on-off. So with all of these, it's about where control is. Where is control of that primary winding? If I have the amplifier sitting on the coil, I can directly go here and get the signal to the transistor. If I don't have the control module here and it's built into the ECU, which many of them are now, I don't have control of that coil, is not sitting on it. It's back in the ECU somewhere. So I don't have a look at the actual control signal. I can look at the primary waveform now, but if I don't get a control signal, remember, it's not going to turn on and off the primary, so it won't produce a primary waveform. No primary waveform, no secondary waveform, no spark. So, working out by visually looking at it, where the control is on them, is important. Because it's going to dictate what type of waveform I'm going to produce. If I scope this and I'm looking for a signal waveform, which is a square wave, I won't see it, I'll see a primary waveform. If I scope this and I'm looking for a primary waveform, I will not see it. All I'll see is a control signal to the base of the transistor. So we're going to take a look in a couple of videos the difference between these two and what it produces. And remember, with all of this stuff, checking the wiring is really important. So while this simple one may not be sparking here, and I'm not producing a primary waveform if I go in here, I want to make sure the integrity of the wiring between here and the ECU is good. The same for this one here. I want to make sure the integrity of the signal wire to the amplifier is good. So what do I mean by that? Have I got continuity on the wire, right? Is there contact between the signal wire on this and the signal wire back in the ECU? So basic continuity testing of a wire, just to make sure it's there. Now remember, we said continuity testing isn't the most reliable way of checking a piece of wire, because if I had 10 strands of a piece of wire and I cut 9 of them and did a continuity check on it, I would still have continuity there because one strand is connected. So it gives me an indication, but it's not a be all and end all for testing a piece of wire. Voltage drop normally is a good test of a piece of wire's integrity, because remember, if I have 10 wires and they take this much space and the 9 of them are cut, what I have here is current travelling down through 10 wires but then squashing into one wire going forward. So 9 of those strands are cut and only one of them is still full and continuous. But I'm going to see a difference between pressure-wise, where all of those 10 wires try to squash into one wire. It's going to cause me a voltage drop difference between them, like on a pipe with a piece of water flowing through it. So I have a big thick pipe here, or we'll use, say like that. If that's the diameter of my pipe here, and I check the flow between here and this here, there's going to be a difference, because this one doesn't have the same diameter. So there's going to be a pressure difference between this and this. And remember that voltage drop testing is that, looking at a meter, looking at the pressure difference in voltage between where I connect those two pins, right, between here and here. So if I was doing it on this piece of wire here, and I connected here and here, I'd see the pressure difference between these two spots. If the wire is full and continuous, there shouldn't be a pressure difference. So the meter would read 0, hopefully. If 9 of the 10 wires that are in that are cut and only one is solid, I would see a pressure difference, because there would be a pressure build-up where all that current is trying to squash into one wire, or voltage is trying to squash into one wire. So I would see higher pressure this side, lower pressure this side, right? And the meter would display the difference in voltage to me. Okay, so that's basic testing of this stuff. Done with a meter, rule the coil in, rule it out. Remember, if a module is on here, I have to get that module off if I can. Now, sometimes with these coils, it can be quite hard to get them off without breaking them. So great care should be taken with all this stuff, so that you don't actually cause an issue here, because you may have seen some of these where they're now cable tied on to the coil itself. So we broke the actual holder clips You can't just leave it sitting there, but remember, because it's 3 connectors, and as the engine is rattling up and down inside the car, I can cause a bad connection from it. So, using great care if I'm taking them apart, or if I'm taking leads off them. Remember, the leads will squash on, sit on top here now. Even pulling that lead off, I can't pull by the lead, I have to pull by down here around the shroud, and we'll have a look at what tools are used for it and how we get them off safely without actually causing a problem to the lead itself. Alright, in the next video we'll take a look at testing this type and what we see when it's running, and this type when it's running. Okay, that's it for now. Thanks.